Okay, well, it's a great pleasure to welcome Silvia Nagy. I'm probably mispronouncing your name. I'm sorry, Silvia. She's visiting us virtually from Queen Mary in London, and she's going to tell us about different approaches to gravity from Yang-Mills squared. Thank you, Silvia. I hand over to you.
Yeah, thank you. Thank you very much for having me. And yeah, so this is some work in collaboration with Miguel Campiglia, Eric Chacon, and Chris White. And I will just get straight into it. So today I will tell you about two sort of quite different looking approaches to this double copy program. And hopefully we'll get to see towards the end some ideas that we have about unifying. But first, let me just get into the setup if you are not familiar with this, and do please stop me at any time if you have questions at any point during the talk, of course. So just to begin with, the double copy is the idea that we can take gravity and decompose it as a sort of product, which I will go into later what exactly I mean by product, of two gauge theories. And usually we take some Yang-Mills theory or Maxwell. So generally, we just say Yang-Mills. Now, this was inspired by some relations for amplitudes in string theory, and it has had a revival in the context of scattering amplitudes for gravity and gauge theory via this so-called BCJ duality. And of course, the idea in itself is quite beautiful and intriguing, but the reason why a lot of people are getting interested in it is because it gives us kind of a possible tool to simplifying problems in gravity. So in general, gauge theory is somewhat simpler and better understood, at least in certain specific regimes, than gravity is. So then the hope is that if we can understand this product well, and if the product itself is not too complicated, we can use this double copy to translate problems from one setup to the other. And now in even more recent years, this has been extended in many different directions. And this comes with a slight issue or opportunity, depending on how you see it, is that we have a number of different formulations of what we mean by the double copy. And there is this big question about whether there exists a unique formulation. And I will not answer this question in this talk, but I will just give you some sort of general thoughts and how we're trying to go into that direction. So that's generally the double copy. Now, the first aspect that I will focus on is the symmetries. So why are symmetries important? So we care about symmetries because they're important in off-shell construction. So if I want to build the Lagrangian for gravity from Yang-Mills, if I want to build gravity solutions with control over which gauge choices I make, it is important to understand how the symmetries of Yang-Mills copy into gravity. And this has been well understood at linear level, and we can then try to go beyond linear level. And for example, say we want to construct these Lagrangians. I will not show you the details, but just sort of tell you it is possible to do it perturbatively using some techniques that we already know from the amplitudes double copy. The issue here is that when we try to go to higher orders, we learn that we need more and more complicated field redefinitions to map to the standard general relativity description. So in other words, we do not yet have a nice sort of practical map. And this is because we do not have a good understanding of how symmetries double copy beyond some simple contexts. So moreover, I will focus on asymptotic symmetries as well in this first half of the talk, and why these are interesting. So if you're not familiar with them, the idea of asymptotic symmetry. So for standard diffeomorphisms and gauge transformations that we learn about, quite early on in our career as theoretical physicists, we always assume that the parameters, they go to zero at infinity, right? So a lot of things we prove about them, a lot of things you understand rely on that. However, one doesn't have to do that. And if we relax this assumption and we say that at a certain boundary of space-time called null infinity, which is a null surface, these parameters for these symmetries do not vanish and they will act non-trivially. then we get a lot of very nice applications. So for example, these symmetries appear in the study of soft theorems. So what are soft theorems? When I look at scattering amplitudes and I take one of the particles, for example, to have a zero, to go to zero energy, I get some very nice factorizations in the expressions for the scattering amplitudes. So these are the soft theorems, and they are linked to these asymptotic symmetries. Another link is potentially to experiment via this so-called memory effect, which describes the displacement between 2 points in space-time after the passing of a gravitational wave, which is another thing that can be nicely expressed with the aid of these symmetries. And there's already a little bit of a interest in looking at the double copy at null infinity in this context. So this was symmetries and asymptotic symmetries. And the context in which I will be looking at the symmetries today is the self-dual sector. So the reason for this is that we have a nice simplification, and here we have a description of the so-called kinematic algebra, which helps with the double copy, which I will show you in a few slides. So it's basically an additional structure in the Yang-Mills theory, which had not been fully appreciated in the past. So just to kind of give you the constraints, so self-duality simply means that, say, for Yang-Mills, I built the dual of the field strength and I equate it to the field strength itself. And then very similar for gravity, I do the same for the Riemann tensor. So these are the conditions for self-duality. Now I'm just going to introduce a little bit of notation. So we will be working in the light cone formulation. So these are the coordinates that I will be using in the light cone formulation. And here in this light cone gauge, in the self-dual case, the Yang-Mills field has the following form. So 2 of the components vanish and the other 2 can be expressed in terms of a single scalar. Now, here I've hidden the gauge indices. So of course you should imagine the scalar to be transforming under the non-abelian gauge group of Yang-Mills. So this is why it's bolded, because it itself has some indices that I've hidden. So similarly, I could do the same for the graviton, but first let me introduce just a bit of notation to make it all look more covariant. So I split my space-time indices into this X, which is the U and Z bar, and the Y, which is the V and Z. And so this is what the metric looks like. And then I introduce the following tensor, which basically mixes between U and Z bar, and then this pi mixing between the V and Z. So all this notation is just so that we can write the self-dual Yang-Mills field in a slightly nicer form than what I give you here. So this is now my gauge field defined in terms of this tensor pi here. And then similarly, one can show that you can do this for the graviton as well. So at this stage, we can start seeing how a sort of double copy type of structure is starting to arise. So just to show you again here, so this is what I had at the bottom of the previous slide. This is the Yang-Mills field, and this is the gravity field. Now, the important thing to mention here is that these expressions are fully non-perturbative. So even though I wrote this H here, which looks like as if I'm doing perturbation theory, this is actually in the self-dual sector. This is the full non-perturbative metric. Of course, it doesn't describe all possible metrics, only those that satisfy the self-duality condition. But in that context, it is fully non-perturbative. So then once I've written everything in terms of these scalars, I can write the self-duality equations as equations of motion for these scalars. So this is for the Yang-Mills guy, is the equation of motion, and this is for the gravity scalar here. So I hope it's clear enough that this is the bold phi for Yang-Mills, and this is the phi for the gravity. And now I can introduce this Poisson bracket in terms of this tensor pi that I have here. And this Poisson bracket corresponds to an area preserving diffeomorphism, which you can see if you allow a diffeomorphism in the x coordinates. You'll see that this bracket is invariant under that up to unit, so an area preserving diffeomorphism, and this is what we call the kinematic algebra. So now that I've introduced this notation, we see immediately that these equations of motion can be written quite nicely. So for Young-Mills, I have a double bracket where the red one is just the Young-Mills non-abelian commutator, and the blue one is this Poisson bracket, whereas for gravity, I just have a double Poisson bracket. And this was already noticed some number of years ago, and then it was proposed that one can get the...
Sorry, Silvia, I don't understand your double bracket notation. What does it mean? I mean,
yes.
You only have two entries.
Yeah, sorry. So this notation, maybe it helps if you look. So you see, this is the definition of the Poisson bracket, of the single Poisson bracket. So just pi, and then hitting with derivative I and derivative j. And if you look at, you can see my pointer? Okay, good. So if you look here at this equation of motion, you see you have a pi acting on a phi and then another phi, and then I just do the same again. So basically this double bracket is just this expression here. So maybe it's, okay. I'm abusing the notation a little bit just to kind of show the, so I'm acting.
It's just a shorthand. It's a
shorthand, yes.
It isn't really a double bracket as such.
Yeah, it's a shorthand for basically this expression here. So basically you're doing the action with pi, but like twice on basically, you see. So this pi partial k partial l, and then pi ij partial I partial j. So it helps to keep it in mind as a shorthand.
But the commutator was meant to be acting on the Young-Mills indices. So that's just a commutator between the two phi's. Is that what it means?
Yeah. So this commutator, this red one, you mean now?
Yes.
Yeah. This is just the standard commutator. So remembering that these phi's are basically matrices, or you can think of them with the structure constants. And so yeah, this is just acting on the Young-Mills.
This is just a tensor product of the brackets, the Lie algebra, and the coefficients of the Lie algebra. I mean, you have a Poisson bracket under coefficients. So it looks like a tensor product of these two brackets.
Yes, I guess, yeah, you can think of it in that way, yeah.
It won't fulfill Jacobi identity, though.
Sorry?
It will not fulfill Jacobi identity.
Yeah, so you shouldn't think of, this is kind of just a way to represent these equations, basically. So my goal is not to introduce like a new bracket here. You will see that the whole purpose of this is that I'm doing a replacement. So I noticed that in Young-Mills, I have this mixing of the two brackets if I want to express the equation of motion, whereas in gravity, I have basically applying this Poisson bracket twice. So the idea is that I'm turning the commutator into the Poisson bracket. So on some level, you can already see how the non-abelian gauge symmetry from Young-Mills becomes some partial diffeomorphism on the gravity side. And this is kind of related slightly to what's happening in the amplitudes context as well. And the main thing is that you can have nice sort of double copy rules. So what I take, and in this case, the double copy rules are not that I'm not really taking two Young-Mills things and putting them together. You see, it's more like I'm doing a replacement of something. I'm getting rid of the non-abelian gauge thing for Young-Mills and replacing it with something on the gravity side, with diffeo-related thing on the gravity side. So I have these simple rules now. So bracket goes to, commutator goes to Poisson bracket, and this field just goes to this gravity field. So these are very simple. But now we want to look at actual symmetry transformations, because ultimately we wanted to see some asymptotic symmetries as well. So we want to see actual symmetry transformations that transform the fields, and we can't do all of them. We will be restricting to a subset, but in some sense we'll also be going outside the usual symmetries of gravity and Young-Mills, as you'll see in a few slides. But for now, let me just remind you of the notation. So we had this X and Y separation. Remember, A the H were expressed in this way, and all other components are vanishing in the self-dual sector. So then we want residual symmetries that preserve this form. So for Young-Mills, remember this is just a Young-Mills transformation for a gauge field. So I want to preserve the fact that the AI components are vanishing, so this being the xi, then I immediately find it's quite simple to see here that this lambda should only depend on the y components, basically. So the variation of AI should be, sorry, was there a question? No. So the variation of AI also vanishes. So then this is the Young-Mills residual symmetry that I have. You see, it's a subset of the full set of Young-Mills symmetries. And from there, I can also read off the transformation for the scalar field phi. So instead of just writing it as it acts on A, I can just act it directly on the scalar, which describes my Young-Mills field. So I hope this makes sense. Now let me look at gravity. So here it's a little bit more subtle. So I'm not going to show the calculations, but the idea is the same. So again, remember, as I was saying, this is actually fully non-perturbative. It's just that in the self-dual sector, I can split the metric like this, and then this h mu nu just transforms with the Lie derivative on this metric. And I want to preserve the fact that all the components where at least one of the indices is an I will vanish. So only H alpha beta basically survives. Then I get two families of diffeomorphisms. So for now, I will focus on the first family, which has the following parameters. So I have all the psi i's will vanish, and then the psi alpha will be just some function of the y coordinates. And then again, I can read off the transformation for the, sorry, this is a typo, this should be the phi of gravity in terms of this B. So now let me come back to the trying to see if I can write a double copy here. So the idea is that this is the scalar of Young-Mills, and this is the scalar of gravity. And just staring at these transformations themselves, I don't really see a very nice relation yet. However, it turns out that, if you look at them long enough, you notice that if I define this object lambda, which you can think of as the Hamiltonian with respect to the Poisson bracket, I can rewrite the gravity transformation in the following way. So this object here, so for the first term, you can immediately see how one of these guys just becomes this lambda. And for the second guy, you can see that I can now rewrite the nonlinear part of the gravity transformation as simply this Poisson bracket between this lambda and the field itself. So now we see that we can just use the same double copy rules that we had before for the phi's and the commutators, and add a very simple new one where I just map the lambda of Young-Mills to this Hamiltonian lambda of gravity, and then I can get the gravity transformation from the Young-Mills one. So there's this factor r of a half for the first term here, which I will go into some detail later because it's quite interesting when we look at other symmetry. So just wanted to emphasize that this is the first non-perturbative result for a subset of symmetry. So before, we had understood symmetries mostly at the linear level, but it turns out that restricting to this self-dual sector, we can understand just a subset, of course, not the full set, but a subset of the symmetries very nicely double copies in a non-perturbative form. So I wanted to emphasize, so this is the full symmetries, but only like full in the coupling constant, but a subset. Good. So this was good. So here I just wanted also to mention a bit about this factor. So this factor of r here is, so here you see there's this factor of a half when I match between the two, and we can write this in terms of the degrees of this lambda, which counts the order of xi. So now this seems like a little bit of overkill, but we'll see later that we have many other families. This is why we call this the first, and this guy will become important. But this guy is somehow it basically appeared because we were looking at the scalars. So if I was to go back to the actual, Young-Mills and gravity fields, this factor would disappear in the double copy rules. And then just some more details that if I actually want to now preserve, so until now, all I wanted when I was looking at what sort of symmetries I get, just going back here, I wanted to preserve a particular form. So I wanted to preserve this particular form for A and H. But now I want to impose an extra constraint, which we'll see gives us some more structure, is that I want to preserve these equations of motion as well for the scalars, for Yang-Mills and then for gravity. And if I impose that extra thing, so let me just go back, I find that on the Yang-Mills, it still goes through, everything's okay, but for gravity, I have to restrict this B alpha to be a total derivative. And then the Hamiltonian becomes written in this form, and it helps to introduce an operator S such that now the transformations can be written in terms of this S. So we can rewrite the double copy rules in the following form. So this is just a rewriting that helps later on. I haven't done anything at this stage. So I will move on to the asymptotic symmetries unless there are any questions up to this stage. So the main result here was that with the same rules, you can now get a double copy for the symmetries as well, just supplemented by this simple rule here. Okay, good. So then for the asymptotic symmetries, first I'm just going to introduce the coordinates. And I don't know how familiar people are with looking at null infinity and the sort of coordinates we use there. So usually people use something called the Bondi coordinates, and we use a somewhat simpler version of that called the Bondi flat coordinates, because we realize that in that language, it's particularly easy to express these symmetries. So we define this, these U, V, Z, and Z bars from before in terms of these flat Bondi coordinates. And then this is the metric in these coordinates. And then at null infinity, because we are in the self-dual sector, everything is captured by these holomorphic guys. So we just have this for Yang-Mills, the AZ, and for the gravity, everything is captured by the CZZ. And that, oops, sorry, and then we assume a certain fall off for our scalar, so that finally, at null infinity, these are the expressions. So you see things simplify quite a lot, because of course we have taken our radius to infinity at this boundary. So this is for Yang-Mills and for gravity. And then the double copy, in order to define the double copy, we now remember what we said. So the idea of the asymptotic symmetries is that the parameter doesn't go to 0 at infinity. So instead of going to 0, it goes to some function of Z in this case. So for Yang-Mills, I knew that lambda was a function of Y, and I find that it actually has to be a function of the ratio of this V and Z. So it's just a function of Z in the end. And this is a transformation for AZ and then AZ bar. And then here is just a bit of notation. So now everything is graded with respect to the power in R. So this is not intrinsically that important. The idea is just that I can split. So the subscripts here just denote the order in R. So for this operator S, I can split it depending on what sort of function it acts on. I can split it into various orders in R, and then finally the Yang-Mills scalar transforms in the following way. And then also for on the gravity side, for the Hamiltonian, I can do the same, and again just split it into different orders in R, and the same with the Poisson bracket. So here these are more just calculational details. The main result is this thing that I can still write the transformation rules at null infinity in this nice way, which looks very similar to the bulk. Was there a question? Oh. So it looks very similar to the bulk, and the double copy rules are basically the same. And the only subtlety here is that one has to worry about orders in R. So you see this is a lambda 0, and this Hamiltonian is lambda 1, but then the whole Poisson bracket has a weight -1. So that's the only subtlety at null infinity. And then the interesting thing is that, so this is the transformation on the gravity scalar, but now going back to this is the graviton at null infinity, we recognize this transformation as a subset of what we call the super translations at null infinity. So finally, if you don't care about the calculational details, the lesson is that the holomorphic large gauge transformation in Yang-Mills will double copy to a holomorphic super translation in gravity. So this is kind of the lesson from the first family at null infinity. Good. Any questions on this one?
Maybe just to clarify my understanding a little bit, are these super translations area preserving diffeomorphisms?
Are you thinking about the? Were you thinking about these?
Yes, I'm thinking of your comments earlier on area preserving diffeomorphisms. I'm trying to link the two.
Yeah, that's a good question, actually, because now we have a subset. I guess the way I normally think of them is because now we have complexified things. So I find it more natural to think in terms of these complex coordinates at null infinity. So you have the radius direction, and then you have the u, which is basically roughly like the time direction. And then usually what people do is you have these spheres, right? Everything is foliated by spheres, except now we worked in the Bondi flat. So now we have like a complex plane instead of those spheres. We could have done it with the spheres as well, but this just makes things simpler. So I guess the point is that now what we do is we take holomorphic transformations in these complex planes, which we have at null infinity. So that's kind of how I if I wanted to go back to real, how I should think of, I mean, there's
probably are then.
I think that will be true. If you were to go back to real coordinates and think of them in that way, I think they will be good. Because you see, they do come from these, this is for Yang-Mills here, but they do come from the transformations we had in the bulk, and we just give them a certain fall off. So they have to somehow have the same behavior.
Can I make a remark?
Yes, please.
From what I know, null infinity topologically is S2 cross R, the two sphere cross R. And the BMS group consists of SL2C conformal transformations on S2 and functions on S2, which act as translations. So I suppose that what is meant by holomorphic means it considers holomorphic functions on S2. S2 is a complex manifold.
Yeah.
But main point I want to make regarding Lenjo is these transformations cannot be extended to the bulk. There is no natural extension. At least I don't know if any. I tried once. I mean, it acts at infinity, but if you want to act in the bulk, I don't know how to extend it.
Oh, I think that was partly behind my question. I mean, it is probable that they can be, but just that it's unknown what the extension is.
There is no natural extension. At least I claim there is none. But I may be wrong. But from what we tried, I tried some time ago, I could not. Yeah.
Okay.
So one comment here is that indeed in the standard description, you do have this S2s, but here we took a more unusual choice of Bondi coordinates. So we choose these Bondi flats. So here you see, you don't see that S2. But if you did, I think then you would see those SL2 transformations that you mean. And then in terms of going to the bulk, what do you mean exactly? So the way we think of it is as going from the bulk. So we already know what subset of symmetries I want to look at in the bulk and how they double copy. And then I just go from the bulk to this version of null infinity by basically taking a subset of the transformations which fall off in a particular way. So maybe in that sense, could you go back? Just sort of following, sorry?
Just okay, sorry, I was interrupting, go ahead.
No, no, no. I was just wondering if, like, see, following what we do here, this is just a simple example for Young-Mills. See, we said that generically the Young-Mills parameter is a function of these y's, which are v and z. And then it just so happens that we've chosen very nice coordinates here. And now I said, let me look at the subset where lambda is a function of ratios of v and z. So then it just becomes a function of this little z, which I've defined at null infinity. So now I can take my limit, and then this is my lambda at null infinity. So I wonder if could you go back via this route?
I don't know. I think not. But anyway, if I understand your notation correctly, this z, which is you're putting at infinity on S2 at infinity.
No, it's not S2. Sorry, it's not really S2. We flattened S2. You see, this is the metric now. We've just chosen to flatten the S2.
This is the one can write in Bondi coordinates. You can write the full metric. Let's say Young-Mills, full metric like this in the Bondi coordinates. Okay, fine.
In these coordinates, yeah.
In these coordinates.
Sort of, yeah.
When you go to infinity, what remains, if I remember correctly, is only the last term. Okay, S2. Okay, for the S2 part, the last part is when you go to infinity and get Scribe plus, the topology of Scribe plus is S2 cross R. So I imagine that what you have got here, these Z's are coordinates of S2.
No, so we've chosen coordinate. So you can have this S2 cross R is a subset of the possible topologies you can have at null infinity. So there is a choice where it's not an S2. But rather this.
Okay,
sorry?
that I don't understand.
Yeah,
how there is no flex. The bulk metric can be written like this. In any case, in flat space, Minkowski metric can be written like this.
Yeah, so this is just a flat Minkowski metric in these coordinates that I've defined here.
That's fine. In that case, just like radial coordinates, the theta phi give you a two sphere. From what I know, the z and z bar give you a two sphere also. Just change the coordinate from r theta phi to z bar.
Yeah, so I think this, I didn't have time to really go into details here. So when we write okay, so there's some nice reviews, but I think Barnich and Trassert, where one can find these details. When we go to null infinity and we want to have, asymptotic flatness, we take a generic metric. One can write what a generic metric looks like there with conformal symmetry and everything. And we get an expression that depends on a number of parameters. And then a very standard choice that people make is the well-known Bondi coordinates, which are the ones you mentioned, where I've restricted some of that conformal symmetry to have basically R times S2. And that's the one that most people work with, and it's the most standard one. But a different choice that still gives asymptotic flatness, and it still works, but it's less worked with, is this choice, basically these coordinates, where I've flattened the S2 somehow, basically. So it's just a choice of coordinates in this case. So I could have rewritten everything in terms of the sphere, like you say, but we didn't. So one way you can see that is that all these derivatives that I have are just partial derivatives. Maybe you can't see it here. They're not covariant derivatives on the sphere because we've chosen this flat. I mean, maybe we shouldn't have. Maybe we should have worked with just the standard ones.
No, that's okay. Just a couple of comments. By super translations, you mean super translations to BMS?
Yeah. So I mean, now I'm in this context of these coordinates. So this is what I mean here by super translation. So you see the difference maybe that you might notice with the usual formulation is what I meant, that this is now a partial here rather than, but if you wanted to think back in the standard ones, this would be the covariant derivative on the sphere now.
So the super translation group can be defined without, SL2C, the conformal group of the two sphere, SL2C, semi-direct product and gauge transformations on the line. which are so they're given by functions on the two sphere. This does not involve the metric of the two sphere, okay, intrinsically. It just involves the conformal metric of the two sphere. What I mean is, it is not a matter of coordinates. It is there, okay, the BNS.
Yeah, it just will look slightly different, I guess, is what I'm saying. When you look at particularly what delta C looks like, it will look slightly different in different coordinates, but yeah.
Now, one further comment is, it is a bit unclear to me whether this is classical or quantum. If it is quantum, for example, in scattering theory, one does not have any freedom in choosing this function. I mean, you had to give a quantum state for the scattering and take expectation values and then see what happens. But this appears to, you said, I will put some asymptotic conditions. Where does it come from? Classically, you can have, quantum mechanically, it depends on the quantum state you're dealing with.
Yes, I would say the discussion up to here is quite classical in the sense that we're just interested in symmetries of the fields, assuming some standard fall-offs for them. So we haven't gone into the quantum. We haven't gone into that. So I would say, yeah, at this stage you could think of it classically, but of course you can then start thinking about scattering and stuff and what it will do. But at this stage, for the purpose of seeing the double copy, you can just think of it as in the classical context.
Okay, carry on.
Is that making sense?
I'm not sure, because there has been some, well, this is a side statement. There has been some, I would say, very important developments. I can explain. Sorry? There was some noise.
I think someone's microphone is unmuted.
Okay. Jen.
Yeah, sorry, go on.
Jen's iPad. Who is Jen?
Jen.
Jen, I don't know who it is.
So Jens Hopper has joined us.
Jen. Okay.
Who is knows a lot about these things.
There has been, just a side remark, but it may help you, have been what I think is very remarkable developments in, in infrared theory, okay? And by people doing mathematical physics, namely Jens Mund, Rehren, and Schroer, and also by Buchholz, Grass, and somebody else, some third person, okay? And they have also, they find QED and also in QCD. In gravity, they have announced process in gravity. And they get this analog of these scalar fields, okay, which they call infraparticles. Apparently, that has a long history. And this introduces superselection sectors in QED, which they proceed to prove is uncountably infinite number. Okay? And they break Lorentz Poincare invariance. This, except for the vacuum sector, all the others break Poincare invariance. I remember arguing with Ashok, with Ladda, okay?
Oh, yeah, I know.
Alok Ladda, and also arguing with, not arguing, Miguel.
Yes.
And they were saying that somebody, Strominger says there is no Poincare invariance. I think Strominger is simply wrong. Okay? These people have proved this. They checked explicitly that one gets superselection sectors, and this, the analog of what you are writing in scalar fields are actually quantum fields which give intertwiners between the superselection sectors. So the reason for my question was, the asymptotic behavior is not put in. Okay, it emerges from quantum field theory and scattering theory. I think that these are related, but this is just a, sorry, this is a long remark.
Oh no, that's interesting. I don't know exactly the work you're talking about, but maybe we can discuss later. Yeah, I'm not very familiar, but yeah, that sounds interesting. But I think, yeah, so in this context, we didn't worry about this. So this is just, we wanted to present. So the super translation is quite a standard, well, it's a subset of the standard super translations that people talk about. And our goal was kind of to see, can it come from something on the Yang-Mills side? So this was actually the more standard part of the story. And now I'm going to get to the second family, and now things are going to get a little bit more subtle. So remember, the game was that we were now we're back in the bulk for a second. And the idea was that we were taking the expression for the gravity field in the self-dual sector and seeing what sort of residual symmetries we have that preserve this form. So the first family was very simple, but that wasn't the only symmetry. It turns out there's a second family whose diffeoparameters, this is in the bulk, are described here. So it looks a little bit more ugly. Now the scalar of the gravity, it transforms in this way. And again, I can define a Hamiltonian, and this is kind of the transformation now of the scalar. So you see at this stage, things look a little bit ugly. I don't even know what to do with this last term. And the question is, what kind of Yang-Mills transformation will double copy to this? So now we're kind of going the other way a bit, because it looks like on the Yang-Mills side, we've already made use of all the residual symmetries that exist in the self-dual sector. At least it seems like we had. But on the gravity, we have some more. So then, so it helps to first look at it slightly perturbatively, because you build things order by order. So here, I hope it's not too confusing. I've ignored the coupling constant. So I'm just imagining perturbing things in the coupling constants. And then for gravity, this is just like the 0th order, what you would call the linearized transformation. So if I go back to this ugly expression here, basically just this is the linear term, because these are higher orders because they depend on the field. So starting with this guy, so my goal is that I don't want to change the rules, right? I have a set of rules for the double copy that I found. I want to keep the same rules for all the families, all the symmetries that I found, because otherwise it starts, getting out of control of it. So applying these rules, I get the linearized part of some Yang-Mills transformation, and at this of some transformation on the Yang-Mills scalar. And to get to higher orders, one can simply plug this into the equation of motion and basically use it as a seed to find what's the next order in the transformation. So I hope this sort of makes sense. So you take the equation of motion and I say, I want it to be invariant, and then I can work to any order I want to. And knowing the linear guy, it sources the higher order terms. So it turns out that I find the transformation rule for the Yang-Mills scalar, which is not actually a subset of the standard Yang-Mills transformations. It's non-perturbative and non-local, but on the gravity side, the transformation was non-perturbative, sorry, it's perturbative and non-local, the Yang-Mills one, but on the gravity side, we had a nice local transformation. So this was the gravity one. Well, it turns out that we can rewrite the gravity transformation in terms of this Hamiltonian object, lambda tilde, to be like this. This is up to the next order, up to the basically second order into transformation. I have this usual Poisson bracket and then also this second non-local term. So that finally at second order in the transformation, so that the linearized parts I've already shown you here, they double copy nicely. This is how I found the seed for the Yang-Mills guy. And now at the next order, I find these expressions, which now they look, quite a bit uglier than they did for the first family, but it turns out that the double copy rules that I defined for them, they still work. So that's a nice thing. So no matter what the symmetry looks like or how I express it, I can use the same rules and it will double copy nicely. And then you can go recursively to, so because now on the Yang-Mills side, we only know how to write this perturbatively, you can recursively show that these will work at all orders in perturbation theory. So it turns out in the end, we related a perturbative and non-local transformation on Yang-Mills to something that on the gravity side ultimately resums into something non-perturbative. So we thought that was quite nice. Maybe there is some sense in which the Yang-Mills one will also resum, but we couldn't see how. But we just thought it was quite neat that the double copy related these two transformations that are quite different looking. And then the other thing to learn, which we thought was quite intriguing, is that the gravity transformation here was just another subset of the usual diffeomorphisms in the bulk, but the Yang-Mills transformation is not a subset of the standard Yang-Mills gauge transformation. The Yang-Mills transformation here is just the symmetry of that scalar equation that appears in the self-dual sector. So it's inherently a self-dual symmetry somehow. So somehow it seems like the Yang-Mills transformations were not on their own, the standard ones were not quite enough to get even these, these subsets of diffeomorphisms that we find here. So I don't know, is that making sense? Any questions on this? Good. So the idea, now we can go asymptotically. So here I'm not going to go into a lot of details, but for the second family of diffeomorphisms, when we go to this flat null infinity, I find a new type of supertranslation now where the parameter, instead of being holomorphic, is just z bar times a holomorphic function. And the other possibility is that we also get holomorphic superrotations. Now they are written in terms of the scalar, but you could go back to the CZZ and see them in that case. So we get some subsets of some well-known transformations at null infinity. But these superrotations, interestingly, they don't come from any standard Yang-Mills transformations. They come from these self-dual sector symmetries on the Yang-Mills side. Good. And then finally, it actually turns out, so remember, these were the equations that we had in the self-dual sector for Yang-Mills and for gravity. And it turns out that there is actually an infinite tower of symmetries here, of which this first and second family that I showed you were just like the first two rungs in the ladder. So if you're working perturbatively, so if you start with these equations, you want to look for symmetries basically of these equations of motion. So if I start with some symmetries delta of these equations of motion, I can obtain new symmetries delta tilde, which are defined implicitly by the following conditions. So this is the definition for delta tilde in terms of delta. And then of course I have to invert these derivatives. So sometimes I will get non-local things. Sometimes they collapse back, they resum into local things, depending, but more generally at higher orders, they will be non-local when I try to express them. And this is just, in other words, if you're familiar with self-dual theories and integrability, it's just an expression of the fact that we have some integrability in the self-dual sectors, and this is why we have this big infinite tower of symmetries. So now I've just expressed this graphically here. So these are the first two families that I've shown you explicitly, but one can keep going to infinity in the self-dual sector. And interestingly, again, you can show by recursion using this exact definition here that actually the double copy will very nicely continue to hold at all orders when defined on these scalars, and importantly using the same rules as we did in the beginning. So that's kind of the nice thing. So I think this is where I'm finishing with just the first half of the talk. I don't know how much time I have, or it looks like I'm running out of time.
We are relaxed about time.
Well, I don't want to keep you for 2 hours either. So I don't know if, yeah, you can see there. I'm kind of halfway through my slides. So I'm happy to stop here as well, honestly. And if people have questions.
Yeah, well, this is a good time to take questions. If anyone wants to have questions, by all means. But we should continue in a minute. Does anyone want to ask a question at this point? Jens Hoppe and Bernard Nam have joined us. So they're very welcome.
Oh, good. So it's good because the second half is quite separate. So you can follow it without, yes, without I've planned it. It's basically good. So I'm going to now maybe kind of, yeah, forget this side, set it aside, and I'm just going to show you a completely different formulation of the double copy that we've been looking at recently, and then towards the end kind of say some things about how they might be related. Okay, so first here for this, now we'll be looking at classical solutions in gravity, and I have to start with a little bit of notation. I don't know if this is familiar to people or not, so of course please stop me. So I just wanted to introduce the Spinorial formalism in general relativity. So here the idea is that instead of working with tensors and four vectors, we can write everything in terms of two component spinors. When I mean spinors, I don't mean spinors in the sense of supergravity or supersymmetry. So the components are not Grassmannian objects. They're just two component objects transforming under SL2, and then you raise and lower indices with epsilons. And then any multi-rank spinor you can decompose into a sum of terms involving the symmetric guys and Levi-Civita. This is because these capital A and B only run from 0 to 1. So you have a lot of nice decompositions because of this. So for example, any symmetric guy is just a symmetric sum of a product of spinors, and we call these principal spinors. So these one single index spinors. And then the way to get from any tensor to the spinor guys is to just use basically the Pauli matrices. So for example, for a vector V, this you might have seen in the past. And then the idea is that the determinant of this matrix that I've built from V is just related to the norm of V. So in particular, if V itself is null, so its norm vanishes, then this matrix has determinant 0. So I can factorize it as a product of two spinors because when it is null. So I don't know if all of this is very familiar to people. And then also for any spinor pi, I can construct this matrix which corresponds to some null four vector in spacetime. And in GR, this is important because we can associate these to principal null directions in spacetime. So this is just the spinors. Oops, sorry. Good. So now, good. So now what we do is we take the Riemann tensor in gravity. I contract it with a bunch of Pauli matrices. I end up with this object. And again, then using the properties that, the symmetries of the Riemann tensor itself. And then what I said in the beginning about rearranging things as symmetric guys times epsilon tensors, I end up with this decomposition of the Riemann tensor. And then if I am, let me say I am in a vacuum spacetime, so I don't have any sources, and I satisfy the vacuum Einstein equation, then all that I am left with in this case is the Weil tensor. So these this Weil tensor C, so basically only the first line here survives, and all these guys, this is related to the cosmological constant, this is related to the Ricci tensor, so only this line survives, and I have this identification for my Weil tensor. The nice thing to notice here is that in this language, the Weil tensor decomposes into the self-dual and anti-self-dual part of via this is just like the natural way of writing things in the spinor language naturally separates between anti-self-dual and self-dual parts. So this kind of links a little bit with the framework we had earlier, but you'll see that the double copy is quite different still. And then the Weil tensor is constrained by the Bianchi identity, which we can write in this form. So this nabla here, you just imagine as the usual covariant derivative, but you are contracting with these Pauli matrices. Usually this psi is referred to as the Weil spinor, which I think is bad notation for people who also do supersymmetry, but this you will find in a lot of GR literature. Good, so hopefully this is just gravity. As you've seen, we're looking at a simple version of gravity, just vacuum spacetime solutions. Good, so this was gravity. let's do electromagnetism as well. So for now, let me not do Yang-Mills. Let me simplify my life and just do Maxwell at this stage. I take the field strength, and again, I can split it in this form. And again, this is the self-dual and anti-self-dual parts of the field strength. And and then the Maxwell equations just imply these relations here. More generally, I can write these sorts of equations for any for fields of any spin. So these are called the massless free field equations. And the spin of the field is just the number of spinor indices divided by 2. So you see for Maxwell, I have 2 indices here, and for gravity, I had 4, so it was spin 2. Good. So now I can start. So all of this is just to kind of show that what is this useful for. So I can use it to classify different types of solutions in gravity and electromagnetism. So let me just look at electromagnetism. So as I said before, because this guy is symmetric, I can write it as a symmetrized product of these 2 principal spinors. And immediately I see that I have 2 distinct types. So either alpha and beta are different, or they are proportional to each other. So if they are proportional, of course, you can see that I have a degenerate null direction, because there's just a single alpha basically. And then I have solutions with distinct null directions when alpha and beta are different from each other. And then in terms of to kind of picture it more, you can also go back to your field strength, and you can see that in this case, when it's degenerate, you will get a norm 0 field strength basically. Now, going back to gravity, here I have a bunch of different possibilities, right? Because here I have now, because it's 4 component, 4 different spinors, and I have all sorts of different possibilities depending on how I choose the spinner. So this one means that all 4 are distinct, and then I start making more and more of them the same. So type N, for example, they're all the same. Type D is that they are the same in pairs. So this is one use for these spinors, is that they really separate between different types of solutions, of vacuum solutions. Okay, so now in this context of vacuum solution, there's a very nice formulation of the double copy for classical solutions in terms of these spinorial quantities. So this is the Weil spinor here. It turns out it can be written as a very nice product of 2 different Maxwell field strength spinors divided by a scalar function S. And this was shown to hold for type D and type N vacuum spacetime. So from here, these 2 types. Now, of course, a natural question is, can we push beyond and look at these? So you can kind of see intuitively that these guys are more complicated solutions than these ones. And could we push this sort of double copy for more complicated spacetimes? So one way to do this is to first take a detour through a twistorial formulation. So of course there is twistor theory is, very big at this stage, and it has many different applications to amplitude, etc. But for now, I will just show you, the very, very basics that we need to set up the double copy. So you can think of twistor space as the set of solutions to this twistor equation. So these are just the spinors I defined earlier. This is just a derivative. And the general solution in Minkowski space is an object omega of this form, where x is just my spacetime coordinate, but in this language, and omega and pi are constant in spacetime. Then I can define a 4-component twistor from these omegas and pi's. And there's this notion of the location of a twistor in Minkowski space, which is this point x here, and is defined as the location where this spinor field omega vanishes. So of course, from here, I see that I get this incidence relation between omega and pi just by setting this guy to 0. And this equation you can immediately see is invariant under these rescalings, right? So I can rescale the omega and pi by an L, and this incidence relation still holds. So this immediately makes us think of projective space. So if this whole Z is defined up to a rescaling lambda, then I can see that a point X in position space, I can think of it as a complex projective line, or in other words, if you're more familiar with it, you can just think of it as the Riemann sphere. So I have a non-local map where each point in space-time I can think of as a Riemann sphere in twistor space, parametrized by these pi's. So I hope that's sort of making sense. Any questions on this? Good. So now, how to get from twistor space to position space. So it turns out there is a nice transform called the Penrose Transform, where a field phi in space-time can be defined as this integral of some function f in twistor space. So f is a function of these z's that I've defined here, and this rho x says that we are restricting to basically the Riemann sphere corresponding to the point x where I want to evaluate my spacetime point, and then I am integrating over some contour gamma on this when I do this. And now one has to be careful about homogeneity. Of course, the field in spacetime doesn't know or care about, you know, projective transformations and stuff. So the fact that these pi's have a freedom of being rescaled by a lambda means that I must make sure that f itself has a transformation that exactly cancels that, so that the spacetime field doesn't see the rescaling at all. So we see that f has some degree -n-2 with and the number of indices. And just to say, so this can deal with exact solutions which either linearize the equation of motion by some clever choice of coordinates, such as Kershaw. There's certain special solutions where you can choose coordinates such that you linearize the equation of motion, or if you don't know how to do that, then you just have to linearize by hand, and then you'll get an approximate solution. Another nice thing which we haven't really explored is that this also works arbitrarily in conformally flat spacetime, but we haven't looked at that in detail. So one of the reasons why this transform is interesting, so here there are some tricks and some ways of seeing how we can link, you know, the geometry of spacetime to properties of this function f in twistor space. So let me just start with, okay, so we have a field phi, and as I've told you before, I can write this as a product of many different principal spinors and then symmetrize. And then let me assume that this field has a k-fold principal spinor. So what do I mean is that I have this psi guy repeated k times. And then you see that it will vanish if I contract it with n-k+1 factor, but not if I contract it with n-k factor. So I think this you can see quickly. So if I take this object and I contract it with n-k factors of psi, there will be a situation where I'm just hitting these guys here. So then I don't, everything's okay. But if I do n-k+1, one of the psi's has to contract with another psi. And I hope this is clear from what I've shown, but the contraction of a psi with itself will have to vanish because I'm raising and lowering indices with epsilon. So it's basically just epsilon AB, psi A, psi B. So having said that, so we have this relation between the degeneracy of principal spinors and how many of these psi's I can contract with. So now let me look at the Penrose transform. So let me take this space-time field here and contract it with m factors of some identical spinor eta. And then we see that this field phi has at least an n-m+1 principal spinor eta if the twistor function has a single mth order pole. So the idea here is that you see I'm doing this integral over some contour, and at some point pi will go to eta here. So this guy will now vanish, this bracket here, but it will go to 0 as some power of m, and then that can be cancelled by the pole in f. So if f has a higher order pole, then this integral will not vanish, but if it has a pole of order m, then this integral vanishes when I perform the complex integral and I get residue 0. So just all of this is just to say that the degeneracy in the spinorial decomposition of phi is related in a very straightforward way to the order of poles in the function f. So we've taken some geometrical data about our solution and rewritten it into some kind of, I would say simpler data about the order of the poles of this function in twistor space. Good, so then one can finally define, so first let's look at the type D Val double copy, because that's the one that was best studied and best understood. So this is the one I was showing you earlier in space-time. It turns out that this can follow from a twistorial formulation. So if you take two twistor functions, electromagnetic ones of homogeneity -4. So remember, the homogeneity is just -2 minus 2s. So for a spin 1, it will be -4. And then for a scalar, it will just be -2 minus 0. So this guy corresponds to a scalar. I can then build a gravity twistor function in a very similar, in basically the same form as this, by putting together the two electromagnetic guy and the scalar one. And I see the homogeneity works because I have -4 minus 4 and then a -2. So that gives me -6, which corresponds to a spin 2 object, which is what I need for gravity here. So for a suitable choice of these twistor functions, this will reproduce upon doing the Penrose transform exactly the space-time double copy. And the choice is actually quite simple to make, because we can define this Fm in the following way. So we just have some numerical term in front, some constant q, and then just define this contraction in terms of the twistors. And then it has some inverse power of m, which you'll see ensures the right sort of behavior in the poles. So this is what we needed for the type. So this will work for type D and type N, but as I was saying before, this was already understood in space-time. And what we wanted to do is see whether this twistor picture actually allows us to go further. And it turns out that you can. And because I am sort of running out of time, I will not go into the deep details, but it turns out that you can choose, working in twistor space now, you can choose certain representatives for different types of Maxwell functions. So here, remember I told you I have the two possibilities where the principal spinors are the same and when they are different for the Young-Mills, and then I have the scalar functions. And using this, we show that you can construct a twistor representative. So this here, I've given you the expression for type 2 solutions, which in space-time becomes the following expression. So the point here is that to go to more complicated classical solutions in space-time, this very simple formula, that I had here, where it's just a simple product of Maxwell fields then divided by a scalar, is no longer good enough. One has to take a sum of products. But this is something that has actually been observed in a number of other formulations of the double copy. So this doesn't concern us. The point is that seeing what this form is, if you are going at it directly from the space-time, could be quite difficult. And the twistor formulation actually helps you with that, because it has a way of sort of structuring how you write different solutions in terms of the pole structure here. And then it's much easier to see how you can build these combinations to get the right thing on the gravity side. And then you can also do type 1 solutions, which looks a little bit even uglier than this because they are more general. So I didn't write it explicitly. So here is what I was saying earlier, that we've kind of taken quite a difficult sort of differential geometry type problem, and you can reduce it to finding the correct pole structure, which will then help you kind of get a glimpse of what the structure of the double copy should be in more general cases beyond the type D and type N. So I think maybe I went a bit quick there because I was feeling a bit out of time, but that was the kind of in a nutshell the second half. And if there are any questions on this?
I think we'll probably come back to questions afterwards. So.
Okay, so I am basically finished now. I just wanted to give, like, as a last slide instead of sort of future directions, well, it is a bit, I wanted to kind of, so you've seen today from the talk that I've shown you two formulations of the double copy with different aims and also quite different, like, yes, structurally, the way we formulate the double copy was quite different, right? In the first one, we had a set of replacement rules. In the second one, it was an actual product or sum of products of Yang-Mills objects. And now these two are the ones that I've shown you today, but in the literature, there are actually a number of others, one being the scattering amplitudes, which are more like replacement rules that are somewhat similar, but also different from the ones I've shown you here. And then in the linearized approximation, there's also yet another formulation with convolution. So now you might ask, is there like one overriding structure? And I think, you know, we are very far from getting a single formulation, but mainly because people are getting excited and seeing how much can I do in this specific context. But some of us who have been, working on the double copy for a long time, we are starting to think whether, can these things be linked? So here I just wrote a few things. So for example, this 1 and 2, the ones that I've shown you today, the thing here that they sort of had in common, you saw, is that they all start with the self-dual decompositions. And something that we want to pursue in the future for the twistorial formulation is that we just looked at like simpler solutions, which they are exact, but they linearize the equation of motion. So on the Yang-Mills side, all you put in is Maxwell. But we want to look at more general ones. And there is a nice twistorial formulation for this, and it actually works as a perturbation around the self-dual sector. So this kind of links nicely in between the two. Now, between 1 and 3, so these replacement rules that I've shown you in the first half, they are actually, although this is, I guess, only for people who are familiar with the amplitude story, they are actually somewhat related to the replacement rules in the amplitudes, and this kinematic algebra I was talking about does play a role in helping with amplitudes calculations there, although I didn't show you any of that today. I'm just saying it can be connected. And then 1 and 4, so as I was mentioning in the beginning of the talk, there is actually a map for the symmetry transformations that works for the full set of diffuse and gauge transformations, but only at linearized level. And what I was showing you today was non-perturbative, but only a subset. And it turns out that on the overlap, the two, they fit nicely. So they agree. So at least in that context, they are different formulations, but on the overlap, they give the same result. So we were quite happy about that. And then the relation, this is something that might seem even more mysterious, the relation between these exact solutions and the scattering amplitudes map. And this is something that people have been working on. There's a number of groups looking at this, and look from 3-point amplitudes with probe particle, you can see how you can construct some of these exact solutions and how you can link between the amplitudes double copy and the solutions one. And then between 3 and, so the final one is just a link in momentum space. So we are starting to see sort of very small glimpses of things connecting and coming together, but there's still huge amounts of work to do and things to understand. So maybe I should stop because I've already run out of time. But thank you very much. Thanks.
Well, thank you, Silvia, for a great overview of these things. And let's have questions.
I hope the sound is understandable. Some decades ago.
Sorry, we can't hear you at all.
Okay, I give up. No problem.
Oh, maybe you could put it in the chat, or is
No,
there
no,
still sound?
yeah, try again, Werner. We can. I will repeat after him. I can hear him reasonably well. If it's not so clear. If you want to say it again, Werner.
So I think you're.
Some decades ago, there was much work in the self-dual sector of Young-Mills and gravity, tracing transformations, mapping solutions to each other. And can you relate that to the double copy? So
if I rephrase and ask the question again, Werner is talking about some decades ago. There was a lot of work on self-dual ones, and he would like to see if you can relate that older work to the double copy. Did I rephrase it correctly, Werner?
Yeah, in particular the tracing transformations.
So what kind of transformations?
Mapping one solution of the self-duality to another.
Yes.
Okay, good. So, I mean, I'm not sure exactly which ones you are referring to, but I wonder if it's exactly the ones I meant when I was talking about the infinite tower of symmetries here. So here, the idea was that these are symmetries of the equation of the self-duality equations of motion. So, and then you see you actually have an infinite tower of them, because if I have one symmetry delta, I can always define another one delta tilde in this sense. And I think these will indeed map different solutions because they're symmetries of the equations. So for these ones, we did find indeed that at every level you can show that the same double copy rules will apply very nicely, and you can prove it recursively. We didn't look at specific solutions yet. That would be an interesting thing to see how you map, but in principle I believe that they might be the ones you mean.
And I think Werner is looking for maybe the structure of the map that went between them in the double copy as well.
Good. So the map is still the same map. So you will have some, so here I didn't write them explicitly because you see they'll be non-local and quite ugly, and they're kind of defined by recursion. But remember, one example was, sorry, so this is, for example, for the, let me just show you the, sorry, the first family again, maybe. Yeah, so this is, for example, just the first family that we saw, right? And then we saw this nice map mapping the scalar to the scalar, the commutator to this Poisson bracket, and then the lambda to this Hamiltonian that we defined here. And then the idea is that you can then have increasingly uglier versions of this. So if I now go to the second family, this is just, I've omitted the linearized term, so it's just a secular. You see, this is for the second family. This is actually now an infinite, it's like a perturbative expansion that goes on infinitely, but it's a perfectly good symmetry of the equations of motion for Young-Mills and gravity. And this second family was obtained from the first family of symmetries by this mapping that I described here. So if I put in the, for example, that standard subset of Young-Mills that preserved only half the coordinates, if I plug it in here as a seed, I get the second family, and then I can go step by step to infinity. And then the rules are always the same. So the rules are just phi goes to phi, commutator goes to Poisson bracket. The lambda parameter goes to this Hamiltonian that we defined, this packaging of the diffeo parameter that we define on the gravity side. And then it helps to write things in terms of this operator S, which you see that at the linear level. I think, where did I write it in a nice, sorry, let me just go to before the asymptotic. So remember, I wrote everything in terms of these S's just because this factor R appears in the linearized part. There's a half here, and then this is the general formula for R. It's related to the degree of the lambdas in terms of the power of xi. So as you go, as you go to higher order in the families, this R, just this numerical factor would look slightly different. But the idea is that the map is basically always the same. So when I have this tower, sorry, I keep scrolling a lot. So this is the tower of the infinite set of symmetries. To write them out explicitly, so to write out, say, a delta n explicitly would be very ugly in general. But the idea is that the double copy in this form will always work between them. And you can just prove by recursion using these relations. I don't know if does that answer the question?
Yeah, thank you. Maybe it's a tower which had been studied before. Just one person who was interested in it is Carl Lewinbeck, the mathematician. And then we had a Chinese visitor, Ho who worked with Linda Chow on that, but there were various other people. So if you look at the old work and just tracing, then you should be able to find it.
Yeah, so we did see some of the... Yes,
can Benjo repeat the question? I don't understand.
He's just commenting on the older work and giving her references. The names were not so familiar to me, but one of them was Linda Chow. And I think...
Okay, I'll write.
Yeah,
yes,
that would be helpful.
Yeah, so actually I forgot to cite it here, but so this infinite tower we had learned about from, there's some paper by Kangemi and collaborators. And there's, yeah, so these were some old papers where people had separately in like Yang-Mills and gravity found these towers. So these relations here were known already. It would just had not been noticed that they link between the two theories. And a lot of it honestly is just putting it in the right coordinates to see these things. I think the way they were written in the old papers, it was more in this language that I showed you at the very beginning. So sorry, see stuff like this, like you just write things explicitly in components, and then I didn't even give the gravity, but it's similar for gravity, just with two derivatives. And then of course in that version it's not so immediately obvious, because when I write them for you, you know, in this formulation, you can also kind of very quickly think, oh, they must be linked. But I think in the old version, it wasn't so obvious.
Are there other questions? I see Laron is with us as well. Welcome, Laron.
Oh. Hi, Laron.
Hi, Silvia. How's it going?
Good, good.
Who is talking?
I was Laron said hello.
Okay.
I remember.
Can I ask a...
Please go ahead, Bob. Go ahead.
Let me ask a straightforward question. So you are working in Minkowski space, from what I saw. Eyes all over the place. So
sorry, so in this context, you mean?
When you wrote the self-dual equations, there was an eye in the dual equation. So it is only in Minkowski space, but then the field is not real.
Oh, yes, good. So you have to, you have to complexify, and you have to think of the field as complex.
But that is not QED or QCD. That is some complexified QCD, but that is not QCD.
It's a complexification of it, yes, where you can define.
it's not clear to me how it relates to physics.
I think you can go back. You should be able to go back to the, because you see here, these are the coordinates that we're using. You see the coordinates themselves are complex. So here at the top where in the light cone formulation, you see I'm working with complex coordinates. So you should be able to go back to real coordinates where I think then the definition of these things would change, so everything would become real. I think it's just a more convenient language to complexify everything. But we didn't give an explicit map to go back, but I think it should be quite straightforward.
Sorry, one is to impose reality conditions.
Yeah.
To make it a physical metric.
Yeah.
These are solutions of complex general
Yes.
relativity.
Yes. So we from the beginning we're working in the complex, and then you can take a slice, I guess.
And this is also related, I think, by the previous question. The symmetries of the self-dual sector, at least in general relativity, it's an integral system. We know that there is an infinite set of symmetries that have been explored, in particular using Plebanski's heavenly equation.
Yes, yeah.
And I don't know how they map to the symmetries that you are exploring. I think that's what there should be a map, because
yes.
there is an infinite number of conserved quantities.
I can just say something. Ricardo's question, when Penrose wrote the original papers, my remembrance is, well, it is known that to go to quantum field theory, yes, one needs a complex structure on the fields. Okay? One needs a separation of positive and negative frequency parts of the field. Otherwise, one cannot quantize, define the vacuum. So he was thinking of this complexification as a first step in giving a complex structure to the fields, okay, to quantization. That's what he was doing. Okay? Now, if I take a standard scalar field and I do this splitting, one will immediately get infinite number of conservation laws, namely the number operator. How many occupy? That is not generally considered as an infinite number of symmetries in quantum field theory. Okay? Because, for a free field, there are infinite number of conservation laws, namely the number of value of the number operator. Okay? That is not in this polynomial they generate. Okay? But here there must be something deeper. Okay? I don't know. But I want to go back to the topology of the asymptotic space. And I think, let me implicate Denjo also. I remember working with Denjo and then with Brian on compactification of space-time, okay, using Cayley transforms due to Ullmann. Okay? And they tell you what the topology is, it tells quite explicitly what the topology is of Scri plus. And it corresponds to the Cayley transformed unitaries, it corresponds to eigenvalues. I think U having an eigenvalue 1, okay, is a 2x2 matrix. Okay? And I remember working it out, like Brian working it out on the blackboard. Yeah. And it was S2 cross R. There was not, I think I'm quite, well, I'm reasonably confident from my recollection from what I saw. Okay. Okay. By the way, I should say, but Leron is leaving.
I saw. Bye, Leron.
Bye. I enjoyed the talk. Okay, so
sorry, Silvia, I have to
no worry.
And there are this S2 class. So what is a BMS group? Maybe I am telling what I know. Okay. S2 class. Okay. There were papers at that time by McCarthy who pointed out that the BMS group has a very simple geometrical meaning. Namely, on the S2, you have an SL2C action as conformal transformations. And it acts on functions on S2 by standard action, and the functions are of S2 form an abelian algebra, and the symmetric product of this SL2C with functions is the BMS group. Okay, so it was, his papers had the status of a proof. Okay, plus he found irreducible representations of this group. It's very complicated. It is unless you are clever in choosing the representations are not reductive. Okay, there are all kinds of. So he had made an analysis of that. Okay? So this is my statement regarding your questions about the BMS. Okay, I think so. I suspect that what you are calling holomorphic, I simply take holomorphic functions on S2, and SL2C acts on it because SL2C preserves the complex section. Okay, so I think that's what you. I think that's what's happening.
So good. If I was to work, I mean, I agree with, if I was to work in the coordinates where I would see the S2, yes, that's what I would expect. Yeah, the holomorphic.
But this is not a coordinate statement. You're talking
No, I know. I'm just saying the sphere is not visible in these coordinates.
It is. You have BZ, DZ bar. Those are the coordinates on S2 in complex coordinates.
But you don't have, I guess I'm saying you don't have the sphere metric here as you would in the usual Bondi, but maybe that's not important. Do you see what I mean? You don't have the gamma that
No,
you would
but
use.
for flat space, there is no gamma.
Yeah,
It
that's
is
what.
DZ bar.
No. If I did like usual flat space and I worked in the usual Bondi coordinates, this metric would look different, right? I would have a gamma as well here.
I don't remember. Okay.
The sphere metric. All I'm saying is that this is just.
I understand. Okay.
Yeah, that's all. But I agree. But I agree with what you're saying. If I was working in those standard coordinates you're used to, where there's a gamma here, I do agree that what you're describing is what you would see. So these would just be holomorphic functions on that sphere. Yes. It just we found it easier to work in these. Yeah.
What I want to sort of maybe insist is that this is not a coordinates question. It's topological question. Okay? So one can say all this without ever writing coordinates. Okay? This is what happened. So my claim is that these transformations one is making, which will act on this function, this group, the symmetric product of SL2C with functions on S2, cannot, at least I know of nobody who has extended it to the bulk. Okay? It is infinite group, but I don't know how to extend. Okay? So that is remark one, just a remark. And secondly, the phi you are writing here. Okay?
Which phi do you mean this?
Let us say for, well, the published paper deals with Yang-Mills. Okay? So let us say the capital phi. Okay? But this asymptotic behavior again can only be said classic. There is no quantum meaning to writing an equation like this unless you tell the state.
Unless you what, sir?
So in quantum field theory, phi's are operators on some Hilbert space, and they have no value. You have to tell on what quantum state one is evaluating it. Then you get a complex function and you can check asymptotic behavior. So what I want to ask in that context is, this is related to scattering theory, but we know that in scattering theory, the isolated electron, because of infrared effects, does not exist. It is simply wrapped in a cloud of photons. Okay? And there are now a number of theorems that even the mass shell condition on the electron is false. All that one can say is that the minimum mass, the minimum value of p squared is the standard electron mass, but it is clouded by, there's an infrared cloud, like in Fadeev-Coolidge paper. Okay? And they give a fuzzy mass. There is no expectation value of p squared is spread. There is some mean square deviation and so forth. I don't see any of this here. In other words, there is no perturbation theory that I know now when there are these infrared divergences. These papers I mentioned.
Do you mean, are you worried about the phi, or are you, so if I showed you this fall off just for the gauge field and for, would you agree with this fall-off?
I don't know where the follows come from.
So this is just the standard fall-off that I guess people usually take in these Bondi type gauges.
So what is the relevance of that for quantum field theory?
So you're saying why choose?
Yeah.
Why? I guess the idea is that the non-vanishing, as far, I mean, this is just the standard. So first of all, this is the standard fall-off that people work with. So I'm just kind of saying, as far as I understand, so whenever people define asymptotic symmetry or they look at null infinity, this is just the fall-off that they usually take. And the idea is that the non-vanishing components of for the gauge field, for example, will be your AZ and AZ bar, but we're working in the selves, and they correspond to the self-dual and anti-self dual. And for us, you see, we chose a special case where one of them vanishes. More generally, I guess you would also have an AZ bar. So I guess in terms of, yeah, so these are the self-dual and anti-self-dual states, I guess you could think. If
So I had to come back.
And just to cut across you there, I mean, it seems clear to me that in a path integral formulation, they have a clear meaning that at the quantum level as well, and that you path integral, you have some boundary condition on your path integration that is not insisting that the gauge fields go to zero, but they go to these asymptotic forms.
So the problem is the following. Okay? The recent paper, well, also in Fourier coalition, okay? Already in, I should say, Kibbles for equations, Cho long ago. Okay? The problem is the path integral formulation is some mnemonic device, like children learning multiplication table. Okay? We don't know what is happening. We get some answer. Okay? These people have checked. For example, in the paper I told about Mund, Reren, and not Schrödinger, and what is his name? Okay? Bert Schroer. Okay? They show that the quantum state, the scattering theory is, they have not announced, they have announced the scattering theory, but they have not shown it. The standard scattering theory does not apply. Okay? LSZ formulation does not apply, because what is happening is that you have an uncountably many supersolution sectors at infinity. They are all reached non-perturbatively by acting with, I think, exponential of this E phi. Exponential E is the electric charge. Exponential of I times phi acting on the vacuum state. Okay? Original Fock vacuum state. Okay? And they depend upon these coordinates, they change. That is, they are super selected sectors when you change this U and Z. So this BMS is intertwining different super selection sectors. So one cannot expand the scattering amplitude and powers of the coupling constant at all, let alone write a functional integral. Okay? So I don't know whether they have a bearing on this enterprise that is going on. Okay? But they're definitely deep questions. Okay? These papers, I think, are actually opening in entirely new field of quantum field theory. This is my opinion. Okay? I think something, I shouldn't say rebel, it's not changing quantum field theory, but the original Doppler-Haag-Roberts no longer applies because of the lack of the mass gap. Okay? This is my opinion. Okay? But anyway, this may be tangential statements.
No, but that's interesting. I'm not familiar with the one. Who did you say was Grant, and what was the one you were?
Grass. No,
Grass.
The papers which are the paper which is readable. There are many papers. Mm-hmm. They are going. I don't know if there are other questions they should ask. Okay?
I mean, I'm not familiar with them. I will look into them.
There's an old problem. Yeah. There's a whole problem.
I will, yeah.
You can type the references in the chat, maybe.
Yeah, I'll tell.
Werner supplied the references, which are useful.
Just let me tell something. The history of this problem starts with the fact that in the Wigner representation theory of positive energy representations, he had also, what happened suddenly, he had also listed massless representations where the stability group E2 had infinite dimensional, it's not just helicity, you have a whole stack of helicities. And they called it zero mass, what is it? Continuous spin representations. That is a local language. Okay? So these representations are, there is nothing physically wrong, but no one knew how to write a quantum field for it. Okay? One doesn't know because one needs some intertwiner between this E2 representation and a coordinate representation of SL2C. Okay? That's how we write the Dirac field. Okay? Then came Ingvason, who proved that it is impossible to write the standard quantum field. Okay? He proved, he had a proof that one cannot write the standard quantum field with causality requirements for these things. And then as time progressed, Schroer, Mund, others, they proved, Buchholz especially, proved that there are what are called string localized fields. So the notion of causality is changed, but it depends upon a unique vector, which we call E, where E dot E is -1 in their metric. So this is giving you the de Sitter space, or 3+1. So E dot E equal to -1 gives you the de Sitter space. Okay? So they constructed the field depending on this E and generalized the notion of causality and locality for this infinite dimensional representations. Then and they pointed out for at least 3 years now that one can write these fields also for standard quantum fields, including QED and QCD and gravity. 2 weeks ago, there appeared a paper by this paper, Jens Mund, Reren, and Schroer, where they have constructed an explicitly soluble model where the Dirac field, the charge field, completely dressed by the infrared cloud, is explicitly written down. Okay, it is not a local field. It depends upon the coordinate x, okay, plus this direction E, which they call string direction. Okay, this direction gives rise to a scalar field in their construction. It depends simply on E. Okay, and this phi of E, the scalar field, looks remarkably like what Silvia has been writing now. Okay? The properties seem quite similar, and exponential I phi, depending on this E acting on the vacuum, generates a superselection sector. I mean, you change E, the superselection sector changes, and E gives you or smeared E gives you the infrared cloud of the electron. So this reproduces the original Kibble results and Faddeev coalition so on, and it also tells what is happening. And they prove Poincare group is broken. My feeling is that this is the phi that is being written by you, for example, others, is this phi. Okay? But it depends on E, so it depends on the coordinate of the de Sitter space, which is exactly the same as S2 cross R. Topologically, it is exactly S2 cross R. So this asymptotic situation persists also on Sky Plus. And they discuss in their paper this fact. Okay? And you have the action of the BMS group and so on. But this BMS is intertwining different superselection sectors. These are developments only about 2-3 weeks ago, but I think it is very deep. Okay? It has, my opinion is it throws light on measurement theory, okay? Because the phis generate an abelian algebra as an algebra, and one knows from other considerations that one can experimentally observe only abelian algebras. Okay? This already goes back to Bohr. Okay? The abelian algebras are telling you about classical theories. Okay? So it naturally emerges. It's not put in. One is not changing QED, but this happens. Okay? And QCD also, and they say they have also done it for gravity. That I don't know. Okay? So this is the history. I'm sorry that I have been lecturing, okay? But I want to draw attention to these papers, which I consider very important.
This is the one that Danjo just put in.
Right.
Okay, yeah, thanks. I'll have a look. Yeah, that sounds very interesting.
I think that is going to
Particle.
have a very strong impact on quantum field theory. Functional integral, personally, I don't like functional integrals. I think they are, it is like our friend Joost once said that the knowledge of quantum field theory has been reduced now to a knowledge of Greek and Latin alphabets. Okay? Quantum field, there's some functional integrals like that, some rules, but one does not talk about what are you observing, what is the domain of the operators, what is it acting. Doesn't tell.
I think the questions become different, Val. That's one can in principle go back, and it clarifies lots of things.
That's
for,
not
at least
true.
for some of us.
That's not true, because you have to check things like reflection positivity, and in many of these cases they are not checked. Okay? So one does, for example, there were papers by Susskind that non-commutative geometry is incompatible with causality. Shiraz, Minwala, and somebody. Then one checked what is happening, what are they talking? They were writing functional integrals in Euclidean space and applying formal rules. Okay, they were getting contradictions. Then they withdrew the paper, because then I think Sergio Doppler was, and also the Rome group was very upset, and Friedenhagen, they were very upset because they had explicitly proved that nothing like that happens in Minkowski space. Okay? And they were just doing manipulations with functional integrals. So I think the functional integral is a bad place to start physics. Or maybe it's like by hearting multiplication table. After a while, one should move away and do something more. I am not looking for maths rigor, but I am saying that there are issues which come up, okay, which functional integral conceals. But anyway,
I agree with you to a certain extent, but I think it gives additional insights as well, which are clarified.
One has to use several different ways of cooking the answer. Okay, that is
sure.
So that's not an issue here. But these developments, they are not. From what I saw, these papers are not heavy mathematics. The calculation is very quite simple. Jens Bund paper calculations are quite simple, straightforward, we can understand, and they prove that the supersymmetry sectors are orthogonal. Okay? And they illustrate what is happening in two-dimensional case, okay? 1+1 case, where the quantum field theory is soluble, and in that case, the asymptotic directions E give you exactly the Rindler wedge. Okay? In 1+1, and it turns out, that's what I just checked, that you get the Rindler wedge, the vacuum state restricted to the Rindler wedge, as in the usual case, in 1+1, then it is a thermal state. So from the very start, you are dealing with the thermal state on the electrons. Okay? In 1+1, one cannot apply perturbation theory because it is thermal state. Electron is clouded with photons. Yeah. So it does not even have a sharp mass, sharp spin. Even spin statistic theorems are affected with dimension. Yeah. And you seem to get something like braid statistics, but they cannot explode. I think I'll stop here. I have talked too much. The double copy results are very interesting. I don't know what is happening there, but I also don't know how they connect to quantum field theory, standard quantum field theory.
It remains to be seen, Bob, I think.
Yeah, I think we didn't make any claims about that at this stage. We didn't. We were staying classical the whole way through, and didn't make any.
But what intrigues me is
you know that there is nothing classical, everything is quantum.
Yeah, okay.
The burden
But
is on us.
yeah,
Burden is on us to derive the classical answers.
Yes,
Sure.
no, this is true. But what intrigued me is the possible connections which looked deeper to area-preserving diffeomorphisms, and the connection of that with your Yang-Mills. I mean, Ian Toppe, who was here for a little while, he had arguments as to turning area-preserving diffeomorphisms into SU infinity, that the close relation between the two. So that there are tantalizing connections suggested in that literature and in other deformations in non-commutative geometry, which I was alluding to connections between area-preserving diffeomorphisms and Yang-Mills. It also crops up in quantization of membranes. So it looks like there's a potential for something richer there.
that there's more. Yeah. I mean, this was actually found a while ago, well, some number of years ago, just the fact that this symmetry exists in Yang-Mills itself. But then at the level of transformations of the fields, it had not been, yeah. But it's a nice, I mean, it seems to be appearing in the self-dual sector, but then people have done some work in looking at how to go beyond that. And there are some attempts in seeing whether these sort of algebras, obviously they'll be slightly different, they appear beyond the beyond self-dual in Yang-Mills. And it seems, because I think that's something that would give you some deeper understanding of whether there is some elegant, you know, non-perturbative, nice double copy in the full theory. And there is a bit of her, but there isn't, yeah, it's not as sharp as and as nice, I think, yeah, as in the self-dual. But yeah, it's something I want to look at.
Yeah, maybe I will stop the recording at this point.
Oh, yes.
Okay.
Going for
And thank you, Silvia, for
yeah, thanks so much for
stimulating us.
Okay.
We hardly need, I'm not sure who joined with the iPhone, but it's where we are. You're welcome. Say hello would be nice, but it's
Connected to audio. Who is it?
I'm not sure who joined with the on the iPhone.
Yeah, but all there.
Right.
Who is it?
Hello.
Is he talking to me now?
He's talking to whoever else is there.
Yeah, I'm just wondering who you are.
There's probably a few people there. So there's 6 participants, right? So these are the people who are there at the moment.
And
You're still recording.
no, I'm not recording, but I'm just wondering who has
because we have
who has popped in to talk to us.
You are recording according to my screen.
Oh, sorry, I thought I had stopped it. No, yeah.